So I'm just going to throw up the lattice energy equation. You do not need to use this equation in any way, shape, or form, but it just makes it a little easier for us to talk about it. So lattice energy is equal to a constant K, charge 1, charge 2, over distance. So Q1, Q2 over D. So they tell us right away that they have the same crystal structure, and the only difference between the two is the distance. It also makes sense because their charges are the same, right? They're both +1, -1 compounds. So all we need to look at is the relationship between E and distance. Okay? So as distance in the bottom of that fraction there gets larger, what is that going to do to your energy? To make it smaller. So there's an inverse relationship between distance and energy. We can tell that because distance is in the bottom of that fraction. So if I want the one with the longest distance, what does that tell me about the energy? Lower energy, okay? So which one's going to have the longest distance? Any questions on how that one works? Or why we don't need actual numbers to do it? Okay, so part B then is pretty straightforward. So all they're asking us here is to use the ionic radii as given to estimate those distances. So you should see that in each box there's two numbers for each one. There's the number for the neutral atom and there's the number for the ion. So we just need to make sure we're using that one. So for NaCl, we're going to use 1.16 for Na. For Cl, we're going to use 1.67, and that should give us something around 2.83. For the Kf, we're going to use 1.52. We're going to add that to 1.19, and that should give us about 2.71. So we get numbers around there? Does that match what we predicted? Yeah, higher energy, smaller distance. Yeah. Okay, so when we look here, it's specifically telling us in part B, use the ionic radii. So that's how I know I need to use the charged ones. And also think about what's happening in these crystals, right? We have the ions that are locked into these ionic solids. That's why we're using the ion distances. Any other questions about the difference between an ion distance and the neutral distance? Okay. Okay, so here we're looking at the steps to construct the Born-Haber cycle, which essentially tells us how we're going to form these ionic solids. So let's just go through here really basically and kind of talk about what's going on. So the first thing we want to assume is that the two elements are going to start in their standard elemental state. So my two elements are barium and iodine. What does barium start off looking like? Yeah, so barium's a metal, so we can assume that it's going to start in the solid state, okay? What's the first thing we need to do to barium? We need to change it from a solid into a gas, yep. Okay, so that's the first thing we need to do. Now, we have barium that's a gas, but it's neutral barium. When barium becomes part of an ionic solid, is it still neutral? No. What kind of ion is it going to be? Yeah, so it's going to be a cation, and how do we know that barium is going to be a cation? What can you tell me about barium? It's a metal. Metals always form cations. How does it get to be a cation? Loses 2 electrons. Can it lose both of those electrons simultaneously? Think about what you learned about ionization energies. Do we just rip off like 6 at once? No, we go through one at a time. So the first thing we're going to do is we're going to take our neutral gaseous barium and we're going to form the first barium cation, so Ba1+. Then we're going to do this again. How did I know I needed to take 2 electrons off of barium? Yeah, so look at the formula, Bai2. You know that iodine has a -1 charge, so this tells us there should have been a +2 charge on the barium. Questions about that? Okay, so my barium is in good shape to be ready to go into the compound. Now we need to talk about what we're doing to iodine. How do you naturally find iodine? What's it going to look like? What's iodine going to look like when you just find it, walk up to it on the street? Solid. Okay, so what we need to do to iodine is we need to get this into the gaseous state, and we want to separate it. Okay, so we want 2 individual I's in the gaseous state. All right, in order to be part of this ionic compound, what do we need to do to our neutral iodine? Make it an anion, so what is it going to need to do in terms of electrons? Yeah. Notice that I'm doing this for 2 iodines. Why am I doing it for 2 iodines? Look at the formula. Why am I doing it for 2 iodines? Because I need to. All right, so now I've got my cation, I've got my anion. All I need to do is put these guys together. Okay, so that's going to be the last step where I actually form my ionic solid. So those are all the pieces. The last thing they want me to do is figure out which of those steps are going to be exothermic. What does it mean for a reaction to be exothermic? It's going to release energy, okay? So the steps that are going to release energy are steps that we consider energetically favored, okay? So things that kind of make sense. So of all those steps, which seems like they would release energy? There are 2 of them, if that helps. So turning solid into a gas is going to require energy because we're changing it to a more energetic state, but going in the opposite direction, gas into a solid, that's going to release energy. The other thing that's energetically favorable here is making that iodide ion, okay? And the reason for that is we know that the iodine prefers to have that negative charge, so these are going to be your exothermic steps. Any questions about that? So every time you do the Born-Haber cycle, it's the exact same idea. We just change the identity of the cation and the anion. So you got to pay attention to charges, but other than that, it's the same. All right. So the first thing we want to make sure we're on the same page for is what does it mean for a bond to be polar? So does anybody have a good kind of working definition of what it means for a bond to be polar? Difference in what? Exactly. And I'm just writing EN for electronegativity to save space. Depending on where you first heard about this, a lot of times when they teach it in high school, they teach that in order to be polar, your difference in electronegativity needs to be greater than 0.5. So you may have heard that number floating around here. But essentially, anytime there's a difference in electronegativity, that means the electrons are distributed slightly unequally. And that's all we really mean by polar, is we have an unequal distribution of electrons. Okay, so if we look at A, and we're looking at the values for boron and fluorine, I know some of you may not be able to read this chart real well, but for boron we have a value of 2.0, and for fluorine we have a value of 4.0. So is there a difference in electronegativity values? Absolutely, that is definitely a polar bond, and which one has the higher electronegativity? Fluorine. Could you have figured that out without this chart in front of you? Yes. So this is a periodic trend, just like radius, ionization energy, and electron affinity. So you should notice that this trend goes in the same direction as ionization energy and electron affinity. And we should see that all 3 of these trends are the opposite of the radius trend. Remember that the atomic radius is largest on the bottom left. So anything that's not radius basically just goes the other direction. So you should be able to kind of estimate this without the numbers in front of you, but having the numbers makes your life a little bit easier. So this is absolutely polar. Okay, what can you tell me about the bond between 2 chlorine atoms? Why does it have to be nonpolar? Yeah, they're the same element, which means they have the same electronegativity value, so they have to be sharing equally. There cannot be a difference in electronegativities. Any questions? I'm going to leave it there because that's essentially as complicated as it gets. Let's try to squeeze in that last one real quick, and that was 8.28.